When a web browser talks to a web server, it follows a simple question-answer pattern called a request-response. A request is like a child raising a hand and saying what they want. It has three parts. Method, the verb that tells the server what to do, such as get bring me a picture, post give me new data, put replace something, delete throw it away. Think of the verb in a sentence, get a candy. Headers, a list of extra information like the child's name, how tall they are, or whether they have an allergy. In HTTP headers you might see host:/example.com, which house you are knocking on, or user agent:/Chrome/120, which kind of browser you are. Body, the optional content that comes after the headers, similar to the child handing over a drawing or a piece of homework. For a GET request, the body is usually empty. For a POST, it contains the data you are sending, like a form filled out. The response works the same way back. A status line, like I have the candy, headers, how fresh the candy is, how long it will stay good, and a body, the actual candy image or HTML page. HTTP is stateless, which means each request is treated as a brand new conversation, just like a store clerk, who does not remember you after you leave. To keep track of a user across many requests, we add a tiny piece of data called a cookie. The server says here is a little note cookie with a secret number, and the browser stores it and sends it back on every future request like you always carrying a loyalty card. Tokens, for example, JWT, work similarly, but are usually placed in the authorization header instead of a cookie. A token is like a ticket that says I have paid, you may let me in, and it can contain extra info such as username and expiry time encoded inside. Both cookies and tokens let the server recognize the same person without having to remember anything between requests. The state is stored on the client side and simply sent back each time. A URI, that is Uniform Resource Identifier, is the web street address. It tells the browser exactly where to go. The general shape is scheme://authority/path question query hash fragment. Scheme, for example, HTTP, HTTPS, FTP is the type of road, like a highway versus a bike lane. Authority, for example, example.com:8080 is the city and house number. The optional port is like a side gate number. Path, for example, /book/fiction, points to a specific room in the house. Query, for example, question id equals 42 ampersand sort equals ask, adds extra instructions, like bring the red book id 42 and sort alphabetically. Fragment, for example, hash chapter 3 is a bookmark inside the page, like a page number in a book. Encoding changes special characters, such as spaces, the German sharp S, and the Chinese character can, into a safe form using percent codes, percent encoding. For example, a space becomes %20. This is similar to writing a secret message where you replace tricky symbols with numbers so the mail carrier can deliver it without confusion. When a browser wants to talk to a server, it first creates a TCP connection, which is like establishing a telephone call. The steps are: three-way handshake, the client says hello, the server replies hello, I hear you, and the client answers got it. After this, the line is open for data. Data exchange, packets travel back and forth, each acknowledged to ensure nothing is lost. Four-way termination, both sides say goodbye and acknowledge each other. Each program listens on a port number 0 to 65335. Port 80 is the default door for HTTP, 443 for HTTPS, like the front desk of a building. Throughput measures how many bits can travel per second. A simple formula is throughput equals window size divided by round trip time. If the TCP window is 64 kilobytes, 65,536 bytes, and the round trip time, RTT, is 100 milliseconds, 0.1 seconds, then throughput equals 65,536 bytes divided by 0.1 seconds equals 655,360 bytes per second, approximately 5.24 megabits per second. This shows how larger windows or shorter RTTS give faster data rates. HTTPS adds TLS, transport layer security, on top of the TCP connection, turning the telephone call into a secret whisper. Client hello, the browser says I want to talk securely and lists the TLS versions and encryption algorithms. Cipher suites, it supports, similar to offering a toolbox of locks. Server hello, the server picks one lock both understand, replies with its choice, and sends its certificate, a digital ID signed by a trusted authority. Certificate verification, the client checks the certificate's signature, expiration, and that the domain matches, just like checking a driver's license. Key exchange, both sides perform a math trick, for example Diffie-Hellman or RSA, to create a shared secret key without ever sending the key itself over the wire. Finished messages, each side proves they have the same secret by sending a small encrypted hash. Application data, now the channel is encrypted using the chosen cipher suite, for example a ES256 GCM. The cipher suite selection is like agreeing on a language and a secret codebook that both understand. The strongest common choice is used for better security. Caching stores a copy of a resource like an image or CSS file on the client or a proxy, so the next time the browser asks for it, it can be given instantly, just like keeping a favorite toy on your bedside table, instead of going to the store each night. HTTP headers such as cache control :max age equals 3600 tell how long the copy is good. Pipelining HTTP/1.1 lets the client send multiple requests without waiting for each response, like ordering 3 dishes at once and letting the kitchen prepare them together. It reduces the idle time between requests but can cause head-of-line blocking. HTTP2 multiplexing goes further. A single TCP connection carries many independent streams, each with its own ID interleaved together. Think of a superhighway with many lanes where cars frames from different trips travel side by side without waiting for the lane in front to clear. This eliminates head-of-line blocking and improves page load speed, especially on mobile networks. HTTPS security relies on several layered concepts. Certificates are digital passports that bind a public key to a domain name. They are issued by a public key infrastructure, a trusted hierarchy of certificate authorities that sign certificates, similar to a government signing passports. HSTS, HTTP strict transport security, tells browsers only talk to me over HTTPS for the next X seconds, preventing accidental fallback to plain HTTP. It works like a rule on a door that says no plain old mail, only sealed letters. Certificate pinning locks the browser to a specific certificate or public key, so even if a malicious CA were to issue a fake certificate, the browser would reject it. It is like only accepting a lock that matches a known key you have stored, ignoring any new keys the door might claim are valid. Every HTTP response starts with a status code that tells what happened. The first digit groups them. 1XX informational, for example 100 continue, like saying I heard you, keep going. 2XX success 200 OK 201, created the request was completed, similar to here is your order. 3XX redirection 301, moved permanently 302, found the resource lives somewhere else like the shop, moved to a new address, go there. 4XX client error 404, not found 403 forbidden. The client did something wrong, like you asked for a book that isn't on the shelf. 5XX server error 500 internal server error. The server messed up like the kitchen burned the food. The reason phrase after the number gives a short human-readable hint, but programs mainly rely on the numeric code. Proper error handling means the client can react retry on 5XX, ask the user to check the URL on 404, follow the new location on 301, etc. Web servers can serve different versions of a resource depending on what the client can understand. This is called content negotiation. Accept text/HTML application /JSON Q equals 0.8. I prefer HTML, but JSON is okay too. Accept charset UTF-8 ISO 8859-1 Q equals 0.5. Give me UTF-8 if possible. Accept language N-USFRQ equals 0.7. English first, French if needed. The server picks the best match and replies with a content type header. For example, content type text/HTML charset equals UTF-8. Media types MIME types tell what kind of data is being sent. Image/PNG for pictures, audio/MPEG for music, application/PDF for documents. The charset part specifies how text characters are encoded. UTF-8 can represent virtually every character in the world, while older charsets like ISO 8859-1 cover only Western European letters. By negotiating these values, browsers and servers ensure the user sees the right format in the right language without garbled text.